And today we are glad to have Chen-Yu to give us a talk. Chen-Yu is a PhD student at KAUST and is now with the new dev working with Arvin on the networking and systems for machine learning. Let's welcome Chen.
Thank you. It seems there is echo. Do you
Muted.
Okay. I know. Okay. Hi. Oh. Hi everyone. My name is Chen-Yu. I am a PhD student from KAUST, and I am currently visiting Professor Arvin here at UW for a year. So today I am going to talk about my research works on tackling the communication bottlenecks of distributed deep learning training workloads. So to begin with, nowadays, DNN models are state-of-the-art solutions to problems like image classification, language modeling, recommendations, and many more. It's very time-consuming to train these models. So here is a figure showing the petaflops days that is needed to train several NLP models. As a reference, the NVIDIA A100 GPU, which is one of the fastest GPU on market, can deliver about 20 teraflops full precision floating point operations, which would take roughly 500 years to finish training the large GPT-3 on the right. So that is, of course, an overestimate because not all operations are full precision. But in fact, researchers calculated that using A100s, it would have taken 1,024 A100 GPUs to train the GPT-3 model for 34 days. Anyway, we get the idea that it is nearly impossible to train big models with single or even a few GPUs. So if you were thinking that GPT-3 is enormous, keep in mind that it was announced already about 2 years ago in May 2020. Later on in September 2021, Microsoft and NVIDIA introduced the even larger Megatron Turing energy. So if we plot model size versus the time they are announced, we observe a trend, a clear trend that models are becoming larger and larger. In the past 4 years, there's more than 5,000 times increase in model size. So as a result, distributed training is widely adopted. So there are two orthogonal approaches to do distributed DNA training, which are model parallel and data parallel. Model parallel splits the model among different workers, and it needs to transfer the intermediate state following the model's forward and backward passes. Data parallel trains the same model on different workers with different data batches, and it synchronizes the model periodically for consistency. One can also combine model and data parallelism and further apply the idea of pipelining to maximize resource usage. So for this talk, I will mostly focus on data parallel, and I will go deeper in it soon. But in general, distributed training approaches all require communication among workers, and it happens that the communication can often be the bottleneck. So this figure is showing the weak scaling results of training different models with data parallel settings. The scaling factor in the y-axis is the time elapsed for training with n nodes divided by n times the time for training with a single node. So we can observe that communication overheads increase with the number of nodes you used for training. And for larger models, these overhead is more significantly, and the models typically scale very poorly. Like the worst one here, Deep Light, is a big recommendation model. which scales even below 0.1 scaling factor. So this is trying to show the idea that communication sometimes can be a bottleneck. Now, to tackle the communication bottleneck, I am categorizing my work into 3 different perspectives of this problem. So first, I will introduce the work that I call network level optimization. So this work is published in NSDI 2021 called Scaling Distributed Machine Learning with In-Network Aggregation. Okay, so now I will go deeper with the data parallel paradigm. So there are 2 popular ways to perform data parallel training, which is parameter server and or reduce. So first, we have parameter server, which have n workers and parameter servers connected through the networking switch. Parameter server is a centralized service that keeps the global model that we are training. Workers, they have local copies of the model and they train it with different data. So they periodically send these local updates to the parameter server, and then they receive the aggregated updates back. So parameter server solution typically runs on multiple physical nodes to prevent the incast problem, as we can see by these green arrows. But it is also a trade-off between efficiency and additional resource usage. So the other way of doing data parallel is a more decentralized, the all-reduce algorithms. So one of the most utilized algorithm for all-reduce is ring-based, where logically workers form a ring and they send and receive updates to and from its neighbors. But physically, these workers are still connected to the network switches, and all these updates are still go through the switch. Then when they exchange those gradient updates, they process it locally. And one problem of this all-reduce scenario is that the total amount of data flows, the total amount of data that flows through the network is actually proportional to n squared, where n is the number of workers. So it will make the solution hard to scale well. Now, if we look closer at the model at the model synchronization phase, we can observe that actually all updates need to go through the switch. So what if we can do something within the switch? So thanks to the technology, there is the programmable switch, which can perform some operations at line rate. So it can modify the packets, it can do control the packets to do multicast or single cast, whatever. So based on this new technology, we developed SwitchML, and here is how it works. So we see these model updates. We kind of partition these model updates into a small chunk of data, and then we abstract these model gradient exchange process as the aggregators in the switch. So the switch will maintain a pool of aggregators, and the workers, they have chunks of data that they send to the switch. So for example, worker 2 here, when it finishes gradient descent, it sends the gradient updates to the switch. Then whenever worker 1 sends the switch, sends the gradient updates to the switch will perform aggregation on the fly and then sends it back to both the workers. Now, the benefits of this pool of aggregators is that we can actually make all these chunks independent to each other. So while everything is doing, while there is available chunks, any available workers can still send all updates to the switch, while some other workers might fall behind and has lower rate of sending those model updates. Okay.
Well, one question. So, how did you perform the aggregation on switch? Does the switch need larger buffers to do that?
Yeah, this is so those slots are stored in the SRAM of the switch. So
how large are SRAMs?
It's typically about hundreds of megabytes. Yeah, and so this way of abstracting it as pool of aggregators also has the benefit that we do not need to store the whole model on the switch. So this is actually not a limit. So in fact, we in order to achieve line rate, we are only using like a few percent of this resource. Okay.
And like this is typical network switch hardware, like these aren't special switches.
These are special switches, the programmable switches. Yeah.
I'm sorry, I just realized I wanted to ask. Also, I assume the aggregation function is limited to what the switch can perform. Is it just like an accumulation, like an addition, or?
Yeah, this is just addition.
Okay.
Yeah. So the idea is that we want to average those gradient updates and apply to the local models. Yeah. So what we do, so the switch is actually they can only perform integer addition.
Okay.
So we actually convert those floating point numbers to integers.
Oh wow, okay.
And then
there's some element of like quantization.
Yes. Yeah. So I did not go through that in detail
Is it
because
your
of
own
time.
is it your own quantization schema, or are you just using some kind of like standard quantization that would come in a trade like an ML package?
This is there's no fancy quantization. We just kind of multiply the floating point numbers so that we make them all integers.
Oh, so it's like a direct conversion.
Yes.
Okay. How have you evaluated your? I mean, I'm sure you're going to get to this, but like, have you evaluated how that affects the performance of the model in terms of like its accuracy?
We do not find any difference in terms
okay.
of training accuracy.
Nice.
Because what we do is we actually try to find the minimum scale that we needed to scale those floating points.
Are you converting? Is it like 32-bit floats to 32-bit integers?
Yes.
Okay. Interesting. Cool.
Yeah, and they typically different workers, they typically have similar range of the gradient updates. So they don't actually go haywire in this kind of quantization.
Interesting. I'm asking because we think a lot about quantization, but not like in a real formal way. Mostly just I feel like we see people doing quantization all the time, but there isn't, at least I have never run into like a unified framework for quantization that everybody uses. So it's just like interesting to see another example in the wild of people doing quantization, just like using their own schema basically.
Oh yeah.
I mean, it's a really standard one in some sense, but it's cool to see that it just crops up elsewhere too.
Oh, cool. Yeah, actually, we'll also cover some kind of quantization later. But for now, I will just jump to the evaluation part of SwitchML. So SwitchML, it provides a speed up in training throughput up to 2.27 times on 100 gigabit networks. And the baseline here is the state-of-the-art NICO communication library, which implements efficient or reduced algorithms, and it runs with RDMA. So we run these experiments with 8 nodes, each with one V100. We also simulate the case where we have a 10 times faster GPU. So this would mimic like the new A100 or even H100 on the market. So with this kind of simulation, we observe that speed up is often higher because faster GPUs reduce the computation to communication ratio. Okay.
Out of curiosity, what is the light?
Sorry, what is that?
What is the light model? Deep light?
Oh, deep light is a recommendation model.
Oh, okay.
Yeah. Yeah, and I would also note here that the currently the available bandwidth that we can get from public cloud providers are as high as 100 gigabit per second, and this has not changed for many years. And I would say that this also contributes to the communication bottleneck, because we can see that accelerator is advancing quickly while the network speed does not actually move forward as fast as it. So, oh, by the way, I was intentionally trying to cover more contents rather than go deeper into a individual work. So if you guys are interested, we can definitely discuss later on. But the next area of work that I will try to cover is the application level to tackle the communication bottleneck. And these are the natural compression, a quantization method, and also a GRACE. GRACE is a framework for distributed machine learning training. So since we observe communication bottleneck, one of the straightforward solution is, what if we can reduce the amount of communication? So when doing distributed training, workers, they exchange gradient updates, which are typically full precision floating points. Nowadays, there are also half precision floating points. But so the idea is to compress these gradients and send fewer bits. So with that, we propose a quantization scheme called natural compression, which rounds the floating point numbers to its power of 2 neighbors, with the probability that is inversely proportional to the distance to the power of 2 neighbors. So for example, this 3/8 is stochastically rounded to 2 to the minus 1 or 2 to the minus 2. In this case, it's evenly, the probability is evenly because the distance is the same, but you get the idea that when this number kind of goes here, it have different probabilities of rounding to these 2 numbers.
So the 1/2 is the probability that is rounds to.
Oh no. Oh yeah. Here the 50% here is the probability that 3/8 is quantized to 1/4.
No, I wonder what is the purpose of doing the probability rounding schema? Why don't we just round to the closest one?
Yeah, that's a good question. So this is kind of needed if we want to analyze through theoretical convergence. So this is kind of required if we want to prove that under this quantization, the model will still converge with SGD training. Yeah, but I will also talk about it. If we this quantization, it turns out that if we look at how those floating point numbers are stored in the memory, so this is the IEEE 754 standard of storing floating point numbers. So these quantization numbers, interestingly, is exactly extracting the exponent part, and then you add 1 or you don't add anything based on this mantissa. So the mantissa would act as the the probability that we need. So we sample a random number, we compare that random bits with the mantissa to determine if we need to add 1 to the exponent or not. Yeah.
So, sorry, you say that one more time. You sample a random. When you say you sample a random number, you mean you sample a random number that's the number of bits of the mantissa, and then you do a comparison between the two?
We sample a number that is 23 bits.
Okay.
Yeah.
And then you just do like is it greater than or less than?
Yes.
Okay.
Yes.
Interesting. Cool.
Yeah. So doing that, yeah, we can show that this is equivalent to this probability rounding. Yeah. So what we need to store or we need to transfer is only these 9 bits, the sign and the exponent. So this effectively reduces the compression, reduces the data from 32 bits to 9 bits. And it's very lightweight, it's very efficient, given the simple, the expression. So here we apply natural compression on top of in-network aggregation. So SwitchML, so like sorry, we also talk about SwitchML, which actually needs integer type of number to work on. So this natural compression was actually developed in need of this requirement that SwitchML can only process integer numbers. So we tried to develop a quantization scheme that would convert floating points to integers. However, this is a separate work when SwitchML is not actually using this quantization. So this is a separate a follow-up work. But this matches well with SwitchML's requirement. So
just to clarify there, so when you presented SwitchML when you first wrote the paper, it was using the quantization scheme that we discussed before.
Yeah.
But it was actually made, or this actually came up because of, or no, SwitchML came about. No, this came about because of what you were trying to do with SwitchML, and this also works with SwitchML.
Yes.
Okay.
Yes.
I see.
So yeah, this quantization, it does not. It is more general. It can not only run on SwitchML, but it can also run on typical training. But so here you can see that so in the evaluation, we are actually applying it on top of SwitchML, and we can observe a up to 4.7 times speed up over Nico on 8 nodes. So here is the here we have also the orange bars where it is labeled CNet deterministic. So this is a variant which simply rounds the floating point number to the nearest power of 2 neighbor.
So it does not use probabilistic.
Yeah. So this one, it does not generate random numbers. So it does not have those overheads.
Any performance comparison of these methods? I mean, the final accuracy or something.
Yeah, so in practice, we observe no difference in the performance of the trained model. But theoretically, we did not prove that deterministic scheme can converge. So we can guarantee that with randomized rounding, it can converge, but with deterministic, we do not. Yeah, but in practice, we didn't find any difference in the resulting model. Okay. So because there are many gradient compression methods, we also built a framework called GRACE, which aims to provide a unified way of implementing gradient compression methods. So we built this framework, and then using it, we performed a quantitative evaluation of 16 different compressors on 7 DNNs and for 5 ML tasks. So I will just summarize the main findings that no compressors is overall best. So some compressors work better on some kinds of model in terms of speed and also accuracy, but there is no one compressor that so among the 16 compressors that we tested, no one compressor is overall best.
Sorry, and a compressor here in this case, is it a quantization scheme or is it something more broad than that or different?
Oh yeah, we actually categorize the compressors into three categorization, sparsification, quantization, and something hybrid.
I see, cool, okay.
Yeah.
Awesome.
Yeah, so I'm not listing here, yeah, but you can find these in the paper.
Yeah, that makes sense.
So next, the computational overheads of compressions are actually not negligible. So in order to do the compression, you first need to do some computation. And those computations are not negligible, and it sometimes even makes it worse. So sometimes when we apply compressions, we actually see worse performance in terms of time. Yeah, so third conclusion, the DNN architecture and the collective libraries and the bandwidth all have an impact on the training performance.
So Grace is like a benchmarking work, whether it's all these compressors or settings like that.
Yeah, Grace itself is a framework which provides a API for you to implement your own gradient compressor. And once you have implemented a compressor, you can use our script to run a series of benchmarks.
Yeah, but
Yeah.
Do they need to provide the implementation of the compressor? You mentioned that there is also computational overhead of the compressor. So I wonder, did you also generate the compression algorithm, or you need the user to write it by their own?
Oh yeah, so the idea is that we have this framework and we use it and we implement 16 different compressors as kind of an example.
Okay.
So with these examples, user can modify and implement their own ideas, and then they have a standardized baseline to compare with.
Can you give some intuition on like which type of compressors are like better in like which scenario? Like when would you say sparsification is, you know, more helpful versus quantization? Like, does it depend on the bandwidth? Does it depend on the architecture? Like, some intuition there?
So there is, I would say there is no a single clear conclusion that we can draw from these different evaluations, but we do have multiple comparisons in the paper. Yeah, so yeah, maybe we can later on discuss more. Yeah. Okay. So yeah, that's the second level, and third, I call it the code design, that is kind of applying the application level and also utilizing the network level optimization that I talked about. So this work is called OmniReduce. It does efficient sparse collective communication. So we when we're along the work that we do, we observe that many gradients are highly sparse, especially for the embedding layers in recommendation models or language models. So, and for example, here we are showing these different models, the size and its gradient sparsity. So this is an overall sparsity. So this number would change during the training, but we are trying to give a average sparsity that is throughout the training. So you can see that using deep light, you are actually training on a 99.73% sparsity model that is full of zeros. So sparsity here refers to the proportion of 0 elements.
I think this is mainly because in recommendation models, you need to update the user or either embeddings, and only a little bit of them are activated in the batch level.
Yeah, that's exactly the idea. Yeah. So the typical way of trying to do sparse collective. So if you already know that you have a very sparse gradient, then one way you can do it is you perform sparse collective. So you transmit the non-zero values and their indices with altogether. So altogether is a communication primitive that collects all data from all workers. And in order to do this, you need to first convert the dense representation to sparse representation, which means the index value pairs. So for example, this gradient here, we can convert it to the key value pairs of 0, 1, 1, 1, 4, 1, 5, 1, 6, 1, 7, 1. Okay. And then you can do all reduce, all gather, which you collect the data from all the workers, then you combine them in the sparse format, and then you need to convert it back again. Yeah. So this solution is much slower than dense or reduce. So if you just perform or reduce on this sparse tensor, you sometimes will find it more efficient than altogether if the sparsity is not high enough. And sparsity is something that you typically don't know beforehand. So the way that we exploit sparsity is the following. We partition updates into blocks. So here the block size is 2. Okay. And then we include a take that indicates the next non-zero block index. So a 0 block means the elements of the block are all zeros. So we have a tag that shows the next block that is non-zero. So for example, this one is the index 2. So the 2 block, this is non-zero. And then we have all workers send this block to an aggregator. So with this aggregator, we can, so this aggregator is actually the switch. So we can also do these things all on the fly, thanks to the programmable switch. So these aggregators, they perform on the fly, they gather all the next block information, and it also performs aggregation for this block. So now it has knowledge of the next block, the next non-zero block of all workers. It also maintains a table that records the next non-zero block for all workers. So it knows that the next non-zero block that we are going to collect from all the workers is 2 in this case. So it will send this back to the workers, and that the workers will know that, okay, the next block that I'm going to send is 2. So in this case, if you see worker 2, it sees that, okay, I'm going to send the next block of 2. However, the block 2 is a 0 block. So worker 2 does not actually need to send anything. And worker 1 there will only be worker 1 who is sending this block 2. And the aggregator already knows it because it has a table recording that worker 2 has the next block index of 3. So in this scenario, it can send this although it only receives updates from worker 1, but it knows this is complete and can be sent back to the workers. Okay, so yeah, the same process will go on, and then when the process is complete, we have updated the next block to infinity, so that everyone, when they receive back a next block of infinity, they know that this aggregation is done. Okay.
So the basic idea here is
Yeah.
that we ignore all 0 blocks.
Yes.
While the reason we use block is something like we increase the throughput.
That's true. That's true. Yeah. So this would also be so the block size would also be something that we need to tune, because if you have a big block index, then you reduce the probability that this block is O0. Yeah.
And again, all of the logic in the aggregator, that's all happening on the switch itself.
Yes.
What is this is just out of curiosity, what does like the programming interface for the switch look like? Do you like put a little program on something on there?
Yeah, there is. So this programming language is called P4.
Oh, okay, okay,
Yeah.
okay. I know P4, yeah. I've never written it, but I've heard it.
Okay. So it's more like a match case table. So if the commit packet matches some scenario, then you do some operation on it.
Yeah.
Yeah.
Okay. I see. Very cool.
Yeah, so next we perform some evaluation also on 8 workers, and we compare with AG Sparse, which so we use Nico to perform altogether, and with the conversion back and forth with 1% compression. So this 1% compression is applied because if we don't apply these AG Sparse, these models are typically not very sparse. So we were showing that for language models and recommendation models, they are sparse, but for the vision models, they are typically very dense. So these 1% compression is applied to AG Sparse for a fair comparison to omni-reduce.
So, like, what is like a good level of sparsity that you think would be needed to have some? Like, do you need to be like with the 90% sparse, or 99% sparse, or like 50%?
Yeah. So here, for omni-reduce, there is actually nothing applied. So there is no compression for omni-reduce. So in this case, if you see the vision models, these are all densely gradients, and in this case, omni-reduce would give less benefits, but at least the same as the baseline. So I forgot to mention the red line is the baseline, which is using reduce. So because if you think about it, omni-reduce in some sense is like, it's just like SwitchML. If there is no sparsity, if every block is not 0, then you basically send all the blocks, but all the blocks will still go one hop to the switch and go back. So this is SwitchML with some more processing. So it basically does not hurt if the model is dense, but it can deliver huge speed up while if the model is sparse. Okay. So here is this table is showing the actual omni-reduce communication amount compared to if there are all non-zero blocks. So for ResNet and VGG, we are actually sending the same amount of blocks as if there are no sparsity at all. So because while there could be occasional zeros inside these models, they are so dense that the blocks are all non-zero. Yeah, so effectively OmniReduce will send 100% blocks, but for deep light it only sends 0.7% blocks.
That is the block size you're tuning, right?
Yes. And I believe we are using 32 as the block size. Yeah.
One interesting question I have in mind is that I think the performance should be influenced by the number of nodes in the cluster. I mean, the more nodes there are in the cluster, the less sparsity it would result when aggregating the gradients.
Yeah, that's actually true. We do have a section that is discussing this. However, as we observed that OmniReduce does not hurt performance even if there are the model is is all dense. Yeah. So okay, and the other result is the scaling efficiency of OmniReduce. So we were mentioning that the scaling factor is typically very bad for the big models, and OmniReduce can improve that scaling factor by a big amount. So yeah, that's basically it. So to summarize, the distributed data training is often communication bottleneck due to the continuous growing model size and improving accelerators. And my work is trying to tackle those communication bottlenecks from system applications perspectives, and also trying to take advantage of both by co-designing. So these are the papers that I walked through today. I'm intentionally going broader instead of deeper. So if there are any details you are interested, feel free to discuss with me later on. Yeah, thank you so much.
How easy is it for people to use? I mean, obviously this is all research work. I'm assuming it's not like, industry ready, but do you have opinions on like usability of tools like this for the common user? Like are there frameworks that make this kind of thing easy? Are there systems in the cloud that would make this easy? Anything like that?
So this particular work does not, I do not think there is wide adoption of this at the moment. So we are aware that NVIDIA, they actually made their own version of SwitchML.
Oh, cool.
Called Sharp.
Oh.
Yeah, it's not exactly the same, and it has some difference. They are building it with ASICs instead of programmable switches.
Wow.
But the idea is basically the same, that they send traffic to this ASIC, and the ASIC will do the aggregation on the fly and send it back to the workers.
So this is a really dumb question. I'm assuming people in this room would know this. I only know NVIDIA is like they make GPUs. Do they also make like massive like supercomputers that they sell wholesale? Okay, I didn't know that.
Yeah.
Very cool.
Okay, someone has a question.
Hey, thanks for the great talk. Another line of work that is trying to improve on the scalability of kind of massive ML learning models is silicon photonics. There was this paper last year at SICOM called SIPML, where they've built an interconnect using silicon photonics to accelerate the same kind of machine learning applications by basically making massive amounts of network bandwidth available for the different models to communicate more freely. And of course, silicon photonics, given that it's an analog technology, kind of seems to preclude doing anything at the switches to process on the packets. So it seems that these two approaches, like your approach and the silicon photonics approach, are mutually exclusive. If you were to compare what you're doing to what the silicon photonics people are doing, which one of the two do you think is the more viable approach looking forward?
You mean if I can only choose one?
Well, it seems that the approaches are mutually exclusive. So I guess, yes, the answer is you can only choose one.
Yeah, so I am actually not quite familiar with that area of photonic, but I think in terms of, so I'm also not sure if that kind of research they require special hardware, because for SwitchML there is, yeah, I think both notions, they need to introduce some kind of new hardware, but for SwitchML, if you do not, if the P4 program is kind of a module that you can load or unload. So for SwitchML, it's I would say it seems to me that it does not affect the original networking infrastructure. But I'm a bit not sure about these photonic things. I will need to investigate more. But I think, as you said, they seem mutually exclusive. So I don't think we need to really choose between them. And it's a good idea actually if we can combine both and deliver maybe better solution.
Yeah, I recommend reading the SIPML paper by Mandya Gobadi from MIT. So mutually exclusive means you cannot combine the two. At least it doesn't look like it that it would be immediately possible, because silicon photonics requires the signals to stay light, and that means you can't directly process on them because processors are working on electric signals. I think actually from a deployability perspective, your approach is more immediately deployable because Tofino switches are real right now. You can buy them. While silicon photonics is a more forward-looking technology where there are switches available in research, I would say. The technology itself is still being actively researched, so that there's no commercially available product available right now, whereas Tofino switches certainly are commercial products right now.
Okay, thank you for the comment. I will definitely check the paper.
Can I ask the person who was asking? I'm not sure who it was, but how does a photonic packet get switched on the network? Just if you can give a summary, like is there any reading of a photonic packet as it's going through the network?
Yeah, not really. The technology is completely analog. It's in fact a circuit switch network rather than a packet switch one, for exactly that reason, because you can't impose on the light signals. You would have to first translate them back into electric signals, and that's exactly the problem that we have with electric switches, is that takes quite a bit of energy to do, the serialization and deserialization of the packets. If you keep it in the optical realm, then the switching can be done with a lot higher bandwidth, order of magnitudes higher bandwidth. But the drawback is that you cannot read the packets in flight. And you also, because it's analog, if you want to alter the path of the light, you can, but it effectively comes down to rotating a prism in the switch, which has a higher latency, typically on the order of milliseconds, for altering the path. Now, the MIT researchers that I just mentioned have figured out ways using wavelength multiplexing to bring that time down. So you can actually do the kind of switching on the microsecond scale now, if their research work ultimately pans out in production as well. So that makes it more promising, but it seems to still preclude doing any kind of processing in the network on the switches like it's done on in this work, because ultimately we would either have to find ways to build full-on CPUs that can work on optical signals, which I think that work would still take us decades to do, or we have to translate it back into electrical signals, but that brings exactly the same bandwidth problem back that we are currently working with.
Yeah. Yeah, so maybe even to extend the discussion of the last question, like even when photonic networks become, standard and as far widespread as they ever become, they're still going to be, it seems like they're still going to be incredibly specific, and the use cases will be very intentionally designed for very specific use cases, whereas this runs on, in some sense, commercial hardware, like programmable switches may become more prevalent in the common internet and or common use, and so maybe there's an argument that this work is potentially more broadly useful for that reason.
Precisely.
But again,
yeah, you nailed it. I think I would say my worry with the silicon photonics technology is that it is useful right now only for ML training. Now, of course, that is, you could argue, an incredibly useful workload. But it is a specialized, you would have to build out your own specialized network using only silicon photonics switching technology, silicon photonics links, and so forth. And that is a concern from a deployability perspective, because it's premised on the fact that you really have massive amounts of ML training to do for it to be worthwhile for you to invest in that technology. While here, you could argue, and I would be on board with that argument, that Tofino switches are effectively being commoditized and are broadly useful. And so they would just become part of the regular fabric that we'd see everywhere, which would bring their costs down tremendously versus silicon photonics technology.
Good, thank you, Simon.
very much. Great talk.
Thank you, everyone.
Yeah, I'm gonna stop recording and